So benzene is also unsaturated in that it's not made up of only single bonds. There are some double or triple, but in this case, not just double bonds in it. So it's unsaturated, but it doesn't undergo addition reactions as readily as, it doesn't undergo addition reactions at all compared to alkenes. Why doesn't it undergo addition reactions? Why doesn't it want to undergo addition reactions? It's because if it underwent addition reactions, the end product would no longer have this beautifully stable delocalized pi electron system. So a benzene ring, here, a benzene ring is made up of 6 carbons with 6 hydrogens attached, and there are 6 electrons, 1 from each carbon, which instead of being the 4th bond for that carbon, is delocalized around the ring, and they're delocalized above and below the ring, and that makes it surprisingly stable. It's not a stable molecule. This is a common misconception. Benzene is not a stable molecule. Compared to lots of other chemicals, it's actually unstable, but it is more stable than it should be, or than we think it should be. It behaves more stably than it has any right to. This is because it's got this delocalized pi electron system. I'm just going to add that in. Oops. Pi electron system. These 6 electrons, 1 from each carbon, that have been delocalized in the area above and below the plane of the ring. This makes it more stable than it should. It means it doesn't undergo addition reaction, because if it did undergo addition reaction, the addition product would no longer have this delocalized 6 electron pi system. It would no longer be aromatic. And therefore it would be more unstable. So this addition reactions do not happen readily. Instead, substitution happens. So not an addition reaction, a substitution, a swap. Why? Why are we allowed substitution but not addition? This is because by doing it, we can reform the stable ring. So to allow reformation of the stable ring system. So let's think about what happens. I think we've got this across 2 slides, but what happens is we get the approach of an electrophile. Notice the electrophile is positive. I'm going to come back to that in a minute, but we have an approach of an electrophile. A pair of electrons from the delocalized ring system are attracted to the positively charged electrophile, and so move across towards the positive electrophile to make a bond with it. Let's write that down. So that has got, oops, I don't want to do a late, let's do high electron density. That's why the electrophile is attracted to it. Electrophiles are electron pair acceptors, and they are attracted to areas of high electron density. That's what electrophile means, so electron loving or negative loving. So an electrophile is attracted to the area of high electron density. A pair of electrons from that high electron density is also therefore attracted to the electrophile, can move across to create a bond. So this is my electrophile. It is, oh, no, sorry, I just tried to do something. There we go. An electron pair acceptor, which is attracted to the area of high electron density. But in doing this, we have disrupted the lovely stable ring system. That is why, and I'm going to highlight that actually, the formation of the covalent bond, which disrupts the ring system, is the slowest rate determining step. It's because it's led to the loss of the stability. That means my middle step is more unstable. So in order for that step to happen, there's got to be extra energy involved. So this is the slowest rate determining step because it's not possible unless the species has got extra energy or can find extra energy elsewhere. So this is the rate determining step, the slowest step. What happens next? Oh, I'm on highlighter again. There we go. So what happens next? So then we have got a substituted, or sorry, it's not actually substituted yet. We've got a ring system which has got an electrophile on it, and we have disrupted the stable ring system. Notice the position of the delocalized ring. Just because in exams you may lose a mark if you're not careful. The shoulders, I'm going to call them shoulders, of the delocalization should sit as if this were a person and they were his shoulders or her shoulders. The delocalization should sit in line with the carbons that are on the shoulders of the benzene, where the head is where the substitution is happening. So you should get up to, and actually I probably would do that a little tiniest bit more, up to that carbon. Don't go past it, because this carbon does not carry a positive charge. It's got all of its electrons. It's got all of its bonds. It is not charged, but equally these carbons are partially positive charged. So you need to make sure that your delocalization ring C shape does cover them, okay? It's just easy to lose a mark there, otherwise, that's why. Then we need to aromatize the ring. We need to get that stability back again. How does that happen? It happens by losing a hydrogen. I don't need to touch that bond, actually. So the electrons that are involved in the carbon-hydrogen bond are attracted to the positive charge in the center of the ring. So they're going to move towards the positive charge in the center of the ring, ending up with, and it's over here, creating our substituted ring with a hydrogen ion floating around. This step happens rapidly. Why does it happen rapidly? Because we're recreating a lovely stable molecule. So it's going to happen really quickly. The final step is the elimination of hydrogen so that the stable delocalized electron system can be restored. Lovely. Just as a little aside, you don't need to remember this, but I think it's useful. A substitution reaction is an addition reaction followed by an elimination. The challenge is that the elimination or the addition and elimination are creating and using unstable species. So which is something with a full-on positive charge, which is why the substitution continues through addition to elimination to create the full substitution reaction, because then we end up with a species which is stable and neutral, no overall charge. Okay, let's keep